started here. Okay. So we will look at what are called as the MM1 queues, but before that we will just look at the how queues can be classified, characterized and so on. So in general what we have a population of customers, potential customers, and they arrive to the and then to get the service. So we have to model the arrival process. Okay, so it can be deterministic, that is regular arrival in certain intervals, or it can be Poisson, or it can be some following a general distribution. Then you need to also specify, okay, so many different things are there that you need to specify for the queue. This is a very important thing, arrival process. How do we characterize the arrival of the queue? Then the service process. The service time is a random variable. It can be a varying nature, deterministic or exponential or uniform, or it can in general have a general distribution. So these are two things. There may be many other characteristics for a queue. For example, the following thing: the number of servers. 1, 2, there can be many servers, or it can also be infinite servers. Those kind of queues, infinite servers are also important. Then, service rate of heterogeneity of server. All servers may not be of same nature. Some of them may be of may have good service rate, some of them will have lesser service rate. You can have heterogeneity of server. The service rate can also be dependent. For example, they may not have a fixed service rate. If the queue is small, with less number of customers, it may have one service rate. When the number of customers become large, the service rate may switch to a higher value. For example, you could have seen that there may be a server, but there are only 4 or 5 people in the queue. Then they will very calmly serve each one with patience. But the number becomes large, they have to reduce the queue size, so they will start servicing very fast. So the service rate may also be dependent upon the queue length. Okay, so that is one thing. Then the waiting space. Obviously, when a particular customer is under service, then other customers who have arrived has to wait. So that is what we call as the waiting space. Okay. And you may have that there are no restriction on the waiting space. So in which case you may have infinite waiting space, or it can be finite. There are only 10 customers can be waiting. For example, in a doctor's clinic, you may have only say 10 seats or so, you have to only 10 customers can wait. Or you may have a bus. The bus comes, takes the customers and then leaves. So the bus is the server. It may have finite seats. Only those many can enter, others have to just stand in the bus stand. So that can be another characterization. So there may be many other such things. What happens to the server, the customer who comes? If he finds lot of customers in this one, he may decide not to join the queue and may leave. So that effect is called balking. And every customer that arrives may have a deadline before which he expects the service to be completed. Okay? Because he may have other appointment. You, for example, you go to the office, on the way you want to pay some utility bill, electricity bill. So you have assumed that the half an hour you will spend. So if it takes more than that, you cannot be late to the office. So you just, and for the wasted time, then you will just leave. So you may have a deadline before which the service has to be completed. If the deadline expires, you may come out. So customers may get dropped out. So that is called as reneging. Okay. And the number of customers may be changing. So what may happen is, for up to 10 customers standing in the queue, there may be one server. If it exceeds 10, one more server may come and then start joining the queue, serving. For example, in a bank, if the number of people there may be only one teller, and more people come, some other clerk who may be doing a background work, they also come and then join and then start doing the service. So that can also be there. So many variations are possible. Okay. Or if you have a customer, what happens when the waiting space is full? On arrival, the customer has to leave. So customers may get dropped again. Please, can you pass on?
This is already full.
Huh?
It's already full.
You have to, that is why I told you have to
Okay,
do next
on the
one.
back.
Yeah, not back. Next, the same, the next column.
Oh.
You have to create a column there they can sign. Yeah, that's how it has to be. So all these things are there. So accordingly, we can have to specify how the queue is. For that, we use what is called as the Kendall's notation. That specify, okay, that is used to specify the queue and also categorize. Okay. For example, that how the basic notation that you have to give is that you have to characterize the arrival process, the service process, and the number of servers. This is the first important three specification needs to be given. We will assume a case where the arrivals happen according to the Poisson stochastic process, and the service happens according to exponential. The service time is exponentially. This is a very commonly encountered scenario, and the number of servers is 1. So we will take this case. Then we see that if we have a Poisson stochastic process, okay, customers arrive according to Poisson process, then the inter-arrival time has to be exponentially distributed. This is what we have already seen. That is, if the customers arrive according to Poisson, that is the number of arrivals in a duration is a Poisson distributed, then the inter-arrival time has to be exponential. If this is Poisson, the inter-arrival time has to be exponential. We also saw that exponential random variable has a memoryless property. What does it mean? That is, if you start looking at the inter-arrival time for the arrival of the next customer, and at some point the customer has not arrived, you now ask what is the remaining time you have to wait for the arrival of a customer. That remaining time has the same, is also exponentially distributed with the same parameter. Doesn't matter how much time we have been waiting. Okay. So this is called the memoryless property. So the arrival, if you look at Poisson, inter-arrival is exponentially distributed, therefore it has got memoryless property. The service time is a random variable which is also exponential, therefore it also has got a memoryless property. So because of that, we will represent that kind of a queue by means of the MM queue. M stands for memoryless. This M also memoryless. So what the Kendall's notation tells is, in the simplest possible representation, you have it's a 3 tuple. Okay, those specifications are represented using an acronym, and they are separated by means of this slashes. The first one is about the arrival process. Second one is about the service process. The third is the number of servers. You use different notations, symbols, to denote what you really mean. If it is a Poisson arrival process which has got the memoryless property, then you specify that you put M here. If the service is rate is exponential, which also has got a memoryless property, then in the second one you put an M. If the number of servers is 1, then you put it as a 1. So, and call this kind of a queue as the MM1 queue, which means that arrivals are Poisson, service rate is exponentially distributed, and you have a single server. So that is called as an MM1 queue. So in a way, there can be different kinds of queues. For example, you may have MD2 queue, which means that the arrival is Poisson, service is deterministic, and there are 2 servers. You may have an MM infinity queue, Poisson exponential, and then infinite servers. You may also have cases that there are infinite servers. For example, you just go to the library, where there will be so many books. The books of the server. Each reader who goes picks up a book and then starts reading. So the number of servers, there is books, can be very large, assumed to be infinity. So then it is a case of an infinity, MM infinity. Or it can be deterministic, that has a good. Or it can have a general distribution, that is G1 Q. That is, the arrival follows a general distribution. The service time is also generally distributed. You have to specify what it is. It can be uniform or some other distribution. And there is a single server. So these are all the different ways of classifying queue. Then we have got more ways of doing that also. If you want to, if nothing is specified, you assume that the waiting space is infinite. That is automatically assumed. In this MM1 queue, waiting space is infinite. That is, there is no restriction on number of people who can join with waiting. And one more important thing about this queuing, the queuing service discipline. That is, how do you treat the customers? Different customers come, who after completing one service, out of all these customers who are waiting, who would you serve? That is called as the disciplinative policy that you apply for serving one. Normally what you will do is, you will follow what is called as the first come first served method. That is, among the customers who are waiting, the one who has arrived first is the one which is being served. Or one who has been waiting for long is the one who is being served. It is a very fair way of doing that. It need not be the same. You may be last come first served. Or you may have priority among customers, a VIP customer. Okay? Or compared to the low priority customers. You may have a single server with different serving all these queues. So this is the highest priority, second and so on. So you start completing all customers of this one, then you go to the lower priority and so on. So you can have which priority. So there are so many variations of that you can think of the queue. The entire queuing discipline, queuing theory, deals with each one of this and then tries to arrive at all these things. Now we will only concentrate on the MM1 queue in this lecture. So here, what are the things that are important to us? This thing already I have mentioned it here. Okay, so you diagrammatically represent a queue like this one. So this way of denoting that there is a queue where these are all the customers who are all waiting. And lambda denotes the arrival rate. That is the number of customers arriving to the queue per unit time on the average. That is what that is only one specification. There can be many other things. So, whether it is Poisson or something, you can have an arrival. Then, if this denotes the server, and one means there is one server, and the service time and the service rate. If the customers, if there are server is getting customer one after another, what is the rate at which the server services the customer? The number of service completion per unit time is called as the service rate. You use the notation mu to denote. So lambda and mu are two things. In the case of MM1Q, lambda is the Poisson arrival rate, mu is the exponential rate parameter. Okay? And then the quantity that is of interest to us are the following: N, P, N, Q, W. I will just mention what they are. N is the average number of customers in the queuing system. Okay. So if you look at the queuing system, some of them will be waiting, some of them will be undergoing service, one or more. So that entire thing is called as the queuing system. So the average number of customers in the queuing system at any given time, we denote it as N. It is average taken over long time. So there is still will not come here. This is a statistical quantity. This includes those who are waiting, and those under service. Then you may only be interested in knowing on the average how many customers are waiting, not including those getting service. So that we will call it as NQ, because Q first, those who are in the queue, not with the service station. Then T, average time spent by a customer in the queuing system. That is, on arrival, the customer has to wait and join at the end of the queue if it is a first come first serve, and then go ahead, progress towards the server, and then get the service and then leave. From the time of arrival to the time of completion, and that is what we call as T. Similarly, I denoted this as N, which includes the number who are waiting, including the one who is getting service. That is what is called as N. Similarly, the time spent in waiting and in getting service, we are calling it as T. Those who are simply waiting, that we are calling it as NQ. Those, the time spent waiting in the queue, not including the time in getting service, that is called as W. So these are the different things that are of interest to us. Okay. So the first thing that we will look at is, okay, there is one very important thing called the little theorem. Okay, I will mention it later. Okay, probably we will finish that one. So what basically it tells is, for any such queuing system, okay, if you have queuing system, and then you construct a box around it, okay, and treating that as an entity, to which some entities enter, something comes out, okay. If N is the number of entities or customers in that, within that box, within that construct, and T is the time spent on the average in this box before leaving, and lambda is the arrival rate, okay, then N is equal to lambda T. Okay. That is, the number will be equal to arrival rate times the waiting time. Okay. So how do we view it? On the average, this should all our averaging quantities. Okay. So how do we find it? See, lambda is the arrival rate, number of customers arriving per unit. T is the time on the average a customer spends in the queue. So N is the number of customers in the queue. One way of looking at the number of customers in the queue is, by the time someone leaves the queuing system, the number of customers who would join at the back of that customer will be N on the average. Clear? So suppose a person enters here, and then what happens? He progressively moves one after another. Somebody will keep joining at the end, back of the. How many on the average will be behind that customer? By the time the customer leaves, is what you have to find. This customer has spent on the average a time T. So in that time duration T, at the rate of lambda T customers would have come behind this customer when this customer is leaving, and that is what is N is. Therefore, N is equal to lambda T is a general rule that is obeyed. Whether wherever you construct this box, whether you construct it here or you construct it here, this holds good. What we have written is N is equal to lambda T for this yellow colored one. That includes this circle. If it were the other one, then it is NQ is equal to lambda W, which is also something which should be valid. Okay. How do we prove this one? Let's look at two things. One is A of T, another is D of T. This is arrival process, this is departure process. We will plot it against the time. Okay. So what is A of T? A of T is the number of customers who have arrived till the time T starting from 0. Starting from a time T, number of customers who have arrived. So if you plot it, A of T is a non-negative integer quantity. When an arrival occurs, then A of T increases by 1. So maybe the first customer arrives here, then A of T becomes 1. Then the second customer arrives here, then it becomes 2. This is how A of T can be. So this is 1, 2, 3, 4 and so on. So whenever a customer arrives, A of T increases. Arrivals. It's the total number of customers who have arrived. Don't worry about those who have departed. It is only the arrivals. If you look at the departure and look at the total number of customers who have departed the queuing system till a time T and then plot it, then that may look something like this. Here is where the first arrival is. Here is where the second departure, first departure can be. So then D of T becomes 1 here. Then this can be a realization of D of T. That is first arrival, first departure. Second arrival, second departure. Third arrival, fourth arrival. Wherever there is a spike, the length will be only 1 because A of T, D of T increases by 1. They are all counting process. They don't decrease. Okay. So this is how it is. So this is A of T, this is D of T. We are interested in N of T, which is the number of customers in the queuing system at any given time. So what can you tell about N of T? You know A of T, you know D of T process. That's this one. At any given time, the number of customers in the queuing system should be equal to A of T minus D of T. the number of arrivals till that time minus the number of departures will give you the number of what in this one. So it is A of t minus D of t is n of t. So that is precisely the difference between these two curves. So this is n of t. So if you look at n of t, at this point n of t is 1 and here it is 0 because first arrival, first departure, here there is no one in the queue. Second arrival, third arrival, here n of t is 1, it increases to 2, 1, 2, 3. The number increases, decreases and this is how it goes. So this is n of t. We are interested in n. What is n? It is the average number of customers in the queuing system, which is equal to 1 by t, 0 to t, n of tau deta. That is, you find n of t and then average it over a long time interval. So you just find it and then average it. This is what n is. So which means that it is the integration of this shaded area divided by the time, the long time over which you take this integration process. This is what you have to do. Well, this is what we have to find, but how do we find this area? One day is to actually look at the realization of the two. There is another quantity we will look at. What is this quantity? Okay? This is the first arrival. This is the first departure. This is the time spent by the first customer. The second arrival, second departure, is the time spent by the second customer. Third arrival, third departure. It is the time spent by the third customer and so on. So this is how we can interpret it. So the other way of finding this area is that is all the squares t1 into 1 plus t2 into 1. So this plus this plus this plus like that you can construct. So this is t1, t1, t2 and then like that you can. So that is also equal to sum of these time spent by the customer in the queuing system. Let us say the ith customer spends ti time. So the area is also can be equal to t1 into 1, t2 into 1 or sigma ti. Okay. Well, how many customers arrive till time t? If you know, then you can have an idea. Let us assume that all 40 customers have arrived till time t. Okay. Then you find the not 1 over alpha t. It's just equal to 1 by t you have to see. This integral is the area which is also equal to this. In the time t, if alpha t customers have arrived, sigma I 1 to alpha t Ti is also equal to n. Is this clear? Now we can rewrite it. I will put 1 alpha t here by t into 1 by alpha t into sigma I is equal to 1 to alpha t t. But just multiply it and divide it by alpha. Well, so what is this quantity? Alpha t is the number of customers who have arrived till time t, and you are dividing it by t. What is that quantity? Alpha t is the number of arrivals till time t, and you find that and divide it by t is the lambda is the arrival rate lambda. And what is this quantity? That is, you are finding an average over ti, the time spent by the ith customer over all customers who have arrived till time t. That is the average time spent by a customer in the queuing system, which we will call it as t. So this is t. So we have found n is equal to lambda into t, and that is what the Little's theorem tells. Okay? Well, now, this is the one which will make use of it wide. Then, so what we are interested is this quantity. We are going to look into this stochastic process. N of Tt greater than or equal to 0. The number of customers in the queuing system till time t, and we want to characterize it. If you find the average, we will assume it is stationary, and therefore its mean doesn't change, and therefore find that average of N of t at any time t. So that is what is N, that is what the first thing that we have to arrive. Once we know N, other N and T are related using Little's theorem, and T and W will be related because we will see that one. Then NQ, everything can be arrived. So there are 4 quantities in any queuing derivations we are interested in. If you know one, all the other can be found out by using Little's theorem. So getting one is the first thing. For that we are using this. So what is N of T? It is the number of customers. Let's look at the arrivals like this one. So the number of customers at any given time can be, so we will look at a time t1, look at a time t2, and then, and here the number of customers can be something like this. Here it can be like this. This is N of T. So we are first, let us look at N at the time t2 is equal to N2, given N at the time t1 is equal to N. We will ask this question. Conditional probability that at the time t2 the number is N2, given N of t1 is equal to N. That is, here you know that there are 3 customers at the time t1. Here you are asking the question, what is the probability that there will be 5 customers after some. By knowing that there are 3 customers at this time, to find that one, what you have to do is, you should know how many joined the system. From 3 it became 5. What is the what are the ways in which this can happen? That depends upon the number of arrivals and the number of departures. See, if 2 people arrive, you cannot tell from 3 it goes to 5. One would have departed. So there are 2 arrivals, no departure, or 3 arrivals, 1 departure. So many things will lead to this. So it depends upon A of T2 minus A of T1. This is the number of arrivals in T2 minus T1. That is one important quantity you know. Then number of departures. That is this quantity. These are also important. But we know from this counting process. We know from the counting process they have an independent increment property. That is, the number of arrivals in this interval is independent of the number of arrivals in another non-overlapping interval. We saw this property. A of t is a Poisson property, D of t is also a Poisson, will be like that, you will see. So therefore, the number here is not going to influence the number of arrivals or departures here. And therefore these 2 quantities depend only on 3. It will not depend upon what value was there previously. If you know this, you don't need to worry about any of this. That means that if you are nearing to the Markovian nature of the process, given the present, past is not relevant to predict the future. That follows from the independent increment process. There are something more. That alone is not important. You also want to know, well, you have a customer arrived here, he is good. How much, when is the likelihood? It is not only the arrivals that is important. Then this customer will be leaving. That is also important. Okay? Whether will it depend upon the time already spent with the server? No, because the exponential service rate process tells that it is independent. So, the current customer who is undergoing service, how long the customer will stay with the server is also independent of the time already spent by him. That is also memorized. Similarly, the intra-arrival. If you know, one customer has arrived in this one, the system, the time, remaining time for the next arrival is also independent of how much time it has spent. that is also memberless. Because of all these memberless property, we find that this is equal to, and not only this, n of t 0 is equal to n0, and all these things if I put, it is just n of t2 equal to n2, even n of t1 is equal to n. So this is not relevant, which means that n of t, this is a Markov chain. It has the Markovian property. Why we are calling it as chain? Because the state space is finite. So in fact, time is continuous. So it is a CTMC, continuous time Markov chain. But to study it better, we will discretize it. We will not look at continuous time. We will divide the time into small time intervals of size delta, and then look the n of t only at fixed time interval, n at the time, okay, where k can be 2. So that is the only thing we will observe. You will not observe it at all time t. You will observe it only at particular time process, equally spaced, of time duration delta. So if you look at n of t is equal to k delta, which is n of k, you have a discrete time Markov chain, which is n k, k is equal to 0, 1, 2 and so on, which is the same as the CTMC, but only thing is the time is discretized. So if you look at this one, the same memberless property holds good. Therefore this will be a discrete time Markov chain. So this is what we are going to take and then start looking at. So what we have got, n k k we are going to analyze this. So in particular what we are going to look at is, okay, probability that n at the time or I will use differently. Let's look at this one. That is, at a particular time step k, you have n of t is I. At the next time step, k plus 1. What it means, at t is equal to k delta to t is equal to k plus 1 delta. Let us assume that n of t changes from I to j. We want to find what is the probability that n of k plus 1 is equal to j, given n of k is equal to I. That is what we call it as the state transition probability. One time state transition from I to j. How do I denote it? I to j in one time. So we will drop this one. Usually we don't mention this one. So this is Pij, probability that you go from the state I to state j in unit time step. So that is the first thing that we have to find out for this details. Well, now if you look at various things, P00, what does that mean? That is the number at the time, at some time, number of customers is 0, and the probability that the number of customers will increase, will remain 0 is what we have to find out. Okay. Even before this one, we have to know one more thing. Well, we are looking at 2 times from, in a delta time duration, the number of arrivals. This delta is very small, and we know that the arrivals are Poisson in nature and so on. Therefore, probability that, okay, of one arrival in delta, probability of 0 arrivals in delta, probability of greater than 1 arrival in delta delta. All these can be written off following the nature of the Poisson process. We saw that this one, if delta is small, in a case of Poisson stochastic process, the probability that there will be one arrival is linearly proportional to delta, and that proportionality constant is lambda. That is what we mentioned as lambda delta with an error which is order delta. This you can write it like this. In fact, what we did is we started off with this assumption and then derived the Poisson. And probability of zero arrival is 1 minus lambda delta plus order delta. And probability of greater than 1 arrival, when delta tends to 0, more than 1 arrival occurring is order delta. So, if you look at the service, what is the service? It is exponentially distributed. Okay, probability of is mu e power of minus mu t, mu delta. Okay, is what this one would be mu delta. This is how it is. It is probability distribution of the exponential, and here again probability of one departure in delta, probability of zero departure. This also will be like mu delta plus order delta, 1 minus mu delta plus order delta. This will be order delta. Because again it will follow from this one. This we can write it as mu into 1 minus mu delta plus mu delta the whole square by 2 factorial, and then we can expand it like this one. Okay. This is how we can write it actually. And then you can, from this it will follow. All these things will follow. So we will make use of this. So what we are interested is in Pij. We will write one probability that n at the time k plus 1 is equal to j given nk is equal to I. In unit time step, for the number of customers in the system to change from I to j, I and j can take different values. J can be less than I also, because it is the number. It can also decrease and so on. First is P0. No customer in the system. For it to remain as no customer, the only way it can happen is no arrival. There is no other way it can happen. And that is given by this zero arrival, this 1 minus lambda delta plus order delta. And we will look at probability I plus 1. What it means is the number of customers to increase by 1 in a delta duration. Tell me how it can happen. In a unit time step of duration delta, the number of customers to increase by 1. What are the scenarios? I don't want the formula. To tell me a scenario in which number of customers will increase by 1. Huh? One arrival, good on. Correct. That is one way. Probability of one arrival, no departure. Okay, and then good. And then it follows. All these things will lead to just increase by 1. Well, now arrivals and departures are independent. Okay? They will not, number of departures and arrivals will not have any correlation. How many departure take place will not influence who is going to arrive outside bird to the queue. So this is equal to probability of one arrival into probability of one departure. Similarly, these can be factors. So the first thing is probability of one arrival is 1. You now for all these things you have to read it from these 6 formulas and then write it. This is equal to one arrival is what? Lambda delta plus order delta. No departure is what? Tell me. 1 minus mu delta plus order delta. This is the first quantity. And 2 arrivals. Right? Yeah, order delta. Into 1 departure. 1 departure is mu delta plus order delta plus these 2 are also order delta into order delta and so on. Now, if you look at it, if you multiply any function by order delta, it will be an order delta. What is order delta? In the limit delta tends to 0, okay, order delta by delta becomes 0. That is what it means. Okay. So if you multiply anything by order delta, it will be order delta. So if you look at it, what are the functions independent of delta and linear in delta? That is all we will take. This is lambda delta. Lambda delta is that this will be minus lambda mu delta squared into something order delta or whatever it is. And these are all order delta, these are all these will be order delta. And if you add many order delta functions, it will still be order delta. So we can club it all together and then put it one order delta. Now we will of course going to take this limit and drop all order delta. Then in that case, I plus 1 will be equal to lambda delta. Because this delta squared mother is this also delta squared is itself is order delta. What quantity? This into this minus this is order delta squared. So only thing that remains is this. Similarly, if you look at pi I minus 1, what is it? Q length decrease by 1. Only one departure, no arrival, plus probability of 2 departure, 1 arrival, and so on. But if you look at it, and many other things, 1 departure is what? Mu delta plus order delta, and no arrival is 1 minus lambda delta plus order delta, plus 2 itself is order delta, 3 are all order delta, so it's all order delta. So we get pi I minus 1 is equal to, only thing which is linear is mu delta. See, if you look at this one, again this is minus lambda mu delta squared, all these things are all order delta only. So what remains is only this one. Okay? Now, one more thing that we have to look at is pi. That is Q length not to change. Probability of no arrivals, no departure. Plus probability of 1 arrival, 1 departure, and 2, and so on. It goes like that. What is no arrival and no departure? 1 minus lambda delta plus order delta into 1 minus mu delta plus order delta plus this is what? Lambda delta plus order delta into mu delta plus order delta plus all these are order delta terms. So if you only keep up to linear terms with delta, 1 into 1 you will get, minus lambda delta into this one is minus lambda delta, and 1 into minus mu delta, that, and then you have got delta squared and then order delta and so on. All these can be drawn. So Pii is this. So that's it. Now we will have you will write the draw the Markov sheet. Okay. So T00 is 1 minus lambda delta, and if you I to I plus 1 is lambda delta, you can see that I have derived I plus 1 is lambda delta. I minus 1 is mu delta. So that is true for all I. So these are all lambda delta. These are all mu delta. It goes on like that. Then probability of remaining II are to be put in all these things. T00 is little separate. That is why we have separately derived it. P11, P22 are all Pii, which is all this given by this formula. All these are so this is how it comes to. So this is the Markov chain that we have obtained for N of t. This is the starting point. We will solve this Markov chain using the detailed balance condition and derive all these NQs and so on in the next step. Fine. Now you can stop this.